All right, hi everyone. Today we are going to do section 10.3, which is all about using chords inside of circles. So just to recall really quick, a chord is a vocab word that we learned a couple days ago, and it's just a line segment in a circle. So something kind of like this, it's going to have two endpoints on the circle. So that's what a chord looks like. And then over here, we got a couple different pictures. So here's an example. I'm going to start with the picture on the right first. Here's an example of a chord, right? Kind of like what I just drew there. When you have a chord, it creates two arcs in the circle. So we have this arc here, this blue one. This is called a major arc. We learned that the other day. It means an arc that's over 180 degrees. And then we also have this red arc here. This is called a minor arc. That's a smaller arc. It's less than 180 degrees. So anytime you create a chord in a circle like this, the endpoints create these two arcs, right? Now also, if you have a chord that goes through the center point, we know that's called a diameter because it splits the circle directly in half, right? So we would call this one a diameter. And each of these arcs would be semicircles because they are exactly 180 degrees. Okay, so the first theorem we are going to learn today about using chords in circles is called the congruent corresponding chords theorem. And it's pretty self-explanatory. It's kind of common sense. It says that in order for two arcs to be congruent, so let's look at the arc that goes from B to A, so this arc right here, if that arc is congruent to CD, arc CD, the only way that can be true is if the chords that create those arcs are also congruent. And that kind of makes sense, right? Because let's say I take this chord here and I make it like a little bit longer, something like this. As you can see, the endpoints would now create an arc that's much bigger, right? It would not be congruent to the other one. So the only way to end up with congruent arcs is to have congruent chords. So that's what this theorem is all about. Okay, so let's look at our first example. So in this picture, they are telling us that the measure of arc AB is 110 degrees. Okay, so that would be from here to here. So this arc is 110, and they're asking us to find the measure of arc BC. So arc BC would be this arc over here. Now, both of those arcs are created by chords. So if you look at this pink chord right here, see how this chord has endpoints that create that arc? Same thing for the other side, right? So this chord here has endpoints that create this arc. And since the chords are congruent, they're both equal to 9, that means the arcs also have to be congruent. So that means this arc is 110 degrees as well. Okay, and now they're asking us to find arc AC. So AC is kind of like the rest of the circle, right? So it's from here to here. And the easiest way to find that is just using what we know about circles. We know that the entire circle is 360 degrees. So we could just do 360, subtract 2 of those arcs right there, right? 360 minus 220, because that's what you would get if you add these together, 220. And that would give you the leftover measure of that arc. So that would be 140 degrees. Okay, so let's move on to the next example. All right, so in this circle, the measure of arc PQ from here to here, that is 130 degrees. And they are asking us to find the measure of arc RQ. So RQ goes from here to here. Okay, so looking at the picture, here's what we know. We know that this chord is equal to 7, and this chord is also equal to 7. So since both of these chords are congruent, that means the arc that they create, the two arcs they create, are also congruent. So RQ is going to be congruent to RP, so this arc over here. So we know those are congruent. Now, we don't know what either of them are equal to, though. So what we do know is that this is 130. If I know what this entire thing here would be equal to, we could just split it in half, right? Because we know these pieces are equal. So we're going to do 360 minus 130 just to see what would be left. And that gets us 230. And we know that 230 degrees has to be split evenly between this arc and this arc. So we're just going to divide that by 2. So 230 divided by 2 is 115. So that would be the measure of arc RQ. It would also be the measure of this arc over here too. Okay, in our third example, it says we're given this diagram. They are telling you that the two circles are congruent. That's what these little symbols mean. This means circle P is congruent to circle Q. So that means they're the same exact size. They have the same radius, same length here, right? And then they're also telling us that FG is congruent to JK. So those are chords. So since those are both congruent chords, we can use what we know about congruent arcs. So they want us to find the measure of FG. So FG is right here. Well, that would have to be exactly the same as the measure of JK, because they are, both of those arcs are created by this chord right here, and this chord is congruent in both circles. So that would also have to be 80 degrees. Okay, and then the last example on this page involves a little bit of algebra. It says find x. So looking at the picture, they are telling us that this arc is congruent to this arc, and they're just using these little tick marks to show us that, right? So since the arcs are congruent, that means their corresponding chords are also congruent. So we can just take 18x minus 2, and we can set that equal to 52. And then we can just go ahead and solve this equation. So we'll add 2 to both sides. 18x equals 54, and then we can divide by 18. So x would equal 3. Okay, so let's go ahead and turn to the next page. On this page, we're going to talk about the perpendicular chord bisector theorem. So this theorem says that if we have a diameter in a circle, so this line right here from E to G, this is a diameter. It goes right through the center of the circle, as you can see. So if a diameter is perpendicular to a chord, so you can kind of see in this picture here, we have a diameter, and then we have this chord from F to D, and there's a little box here that shows a 90-degree angle. So if a diameter is perpendicular to a chord, then the diameter bisects the chord and its arc. So remember, the word bisect in geometry, it means cuts in half. So it's going to split it perfectly down the middle. So it's going to bisect both the chord and the arc. So that means this piece here from F to H is going to be congruent to H to D, and then the arcs are going to be congruent as well. So arc FG is going to be congruent to arc GD. So let's use this theorem in a couple examples here. So in our first example, they're asking us to find a couple things. I just want to point out some notational differences here. We've talked about this before briefly, but if you see something like this, where it's just giving 2 letters, it says find HK. Notice that there's no M in the front like this one, right? It just says find HK. This means find the length of the line segment HK. So this is not a degree measurement, it's not an arc, it's not an angle, it's the length of a line segment. That's what this notation means. Now if you see this notation over here with the little m and then you see a little arc symbol over it, this is the measure of an arc. So this is one that you're going to use degrees for because it's the measure of an arc. So just keep that in mind, just some slight notational differences here. This one means the length of a segment, this one means the measure of the arc. Okay, so let's start with the length of the segment. So if we're looking at the segment HK, that goes from here all the way over to here. So we know that this piece is 7, and then we can see, as we can see, this diameter, that diameter is perpendicular to this chord. So that means that theorem is true. That means this piece is congruent to this piece. So this side would also be 7, which means the length of HK would have to be 14, 7 plus 7. And then we can do something similar to find the arcs here. So the arcs are also going to be congruent because of that theorem. That theorem says that the arcs are being bisected as well. So this side would equal this side. So we can just take these 2 arc measurements here and we can set those equal to each other. So we're going to have to solve for x first before we can find the measure of the arc. So we're just going to quickly solve for x here. If I subtract x from both sides, I have 10x equals 70. And then we can just divide, so x equals 7. And now that we know what x is, we can plug it back in to get the arc. So they want the arc HK. HK is the whole thing, right? It goes from H all the way to K. So we're going to plug that number into just one piece, and then you can just double it. Or you could plug it into both pieces if you want to, but I'm going to plug the 7 in right here. So 11 times 7 is 77. So the measure of the whole arc, so the measure of arc HK would equal 77 plus 77, so 154. Okay, this next example is very, very similar. If you are watching this from home, I recommend just pausing the video here and trying this problem yourself. But for the sake of time, I am just going to keep going. So to find CE, again, this is the length of a line segment, right? So we're going to look over here. CE goes from here to here. Same kind of thing, right? The diameter, here's the diameter. It's perpendicular to the chord. That means these pieces are equal. It also means that these two little arcs are equal. So this problem is the same as the other one. That means this piece would be 5, so the length of CE would be 10. And then to find the arcs, you can just set those two pieces equal to each other. 9x equals 80 minus x, and then we'll just quickly solve this. I'm going to move this x to the other side. 10x equals 80, x equals 8, and then you can plug that back in. So I'm going to plug it in right here. 9 times 8 is 72, so then the arc CE would be 2 of those, right? So 2 times 72, or 72 plus 72, so 144. Okay, let's look at these next two examples. This one here has a little bit of algebra involved, but it's kind of similar to all the other ones that we've done so far. It says find the value of x. Again, if you're looking at the picture, it's got the diameter, which is perpendicular to the chord. So same thing, we can set these pieces equal to each other, and then we can just solve for x. So 2x plus 1 equals 3x minus 5. I'm going to do this part kind of quickly just because I know we're all really good with solving equations at this point. So we'll subtract the 2x to get that over here. We would have 1 equals 3x minus 5. If you move the 5 over, you would have 6 equals 3x, which means x equals 2. And for this one, you do not have to plug it back in because it just says find the value of x. So we're done. Okay, now this next example is a little different. It's asking us to determine whether segment AB is a diameter of the circle, and then we're going to explain our reasoning. So if we're looking at segment AB, it does look like it's a diameter, right? It looks like it's in the middle, but we don't have that center point. There's nothing that indicates that it is exactly in the middle, so we're going to use what we know about these theorems to determine whether this is a diameter. So looking at the picture, they've marked these two arcs as congruent. So that means this piece here is congruent to this piece here. Now because those are congruent, and we have this chord here, right? And we have this perpendicular angle here, that means that this chord also has two congruent pieces right here, right? So if this piece equals this piece, that means this part of the chord would have to be equal to this part of the chord. So that means this diameter, or this chord in the middle here, this has to be a diameter because it is a perpendicular bisector to QR. It is perpendicular and it's splitting it in half. So that's kind of like the converse. We would consider that the converse of this theorem. This theorem says if the diameter is perpendicular to a chord, then it bisects, right? But in this picture, we can see that it bisects, so we know that it has to be a diameter. So we will say, yes, AB is a diameter. And that's because it is a perpendicular bisector to QR. Okay, so go ahead and turn the page when you're ready. We have one more theorem to learn about. Okay, our last theorem in this section is the equidistant to chords theorem. And remember, the word equidistant, it just means equal distances. So it means the distances are the same. And this theorem says that if you have a circle, so within the same circle, or in two different circles that are congruent to each other, two chords are going to be congruent if and only if they are equidistant from the center. So let's look at this picture here because this picture is kind of hard to look at. I'm going to label some things. We have a chord right here from A to B, and then we have another chord from C to D. And the theorem says that these chords will be the same size, they're going to be congruent, only if they are the same distance away from the center. Now remember, whenever we measure distance, we always measure it so that it's perpendicular. So that's why you see these little right angles here. So when we're measuring if I wanted to measure the distance from this chord to this dot in the middle, we would take the perpendicular distance, okay? So what this is saying is that as long as these two little green pieces are equal to each other, that means that the chords are also congruent, okay? So as long as the distances are equal, then the chords are also equal. So let's use that in a couple examples. Okay, so in the diagram, they're telling us that QR is equal to ST, which is equal to 16. So remember, QR and ST, these represent the lengths of line segments. So let's look at our picture and label that. So they're both equal to 16. So that means this chord is 16, and this chord here is also 16. Okay, so let's keep reading. It says CU is 2x. CU is 2x, and CV is 5x minus 9. Okay, CU, they've already labeled that in the picture for us, right? 2x, and then CV is 5x minus 9. So they've already got those labels here for us in the picture. Okay, and it's asking us to find the radius of the circle. Find the radius of the circle. Okay, so there's a lot going on in this picture. We see a lot of different lines. Remember, a radius goes from the center of the circle and it goes out to the edge. So in the picture, we currently see two of them drawn in right now. So from here to here, and then from here to here, right? Now we do know that this piece from C to U, we know that's 2x, but we don't know this little piece here. So currently, with the way the picture is drawn, we really have no way of finding that radius just with the information that we're given. So I'm actually going to draw in a different radius, because you can do that. You can draw a radius wherever you want, and I will show you why we're doing that in just a second. So I'm going to draw one in from C, and I'm going to connect it to Q, okay? Now there's a few different places you could have done this. You could go from C to Q, you could go from C to R, you could go from C to S, but what we're doing here is we're trying to make a right triangle. So if you look at this picture carefully, and I know there's a lot going on in this picture, I have just created a right triangle. I'm going to shade it in here. So this yellow area is a right triangle. And that's going to be helpful to find the radius, because that red line that I just drew, that is the radius. So I'm going to call it R. I'm going to take that triangle and I am going to redraw it out here, just so it looks a little bit cleaner. So here's what it would look like. The right angle is here. The length of this piece would be 2x. This would be the radius. I'm going to call it R. And then we have this side here. I'm going to call that 8. The reason why I'm calling that 8 is because the entire chord is 16, but we have this diameter that's perpendicular to it, so that diameter is splitting that chord in half. So each of those pieces would be 8. So I have this right triangle. If I knew what x was, then I could just do Pythagorean theorem. I could do 8 squared plus this squared equals r squared. So that's kind of the goal. The goal is to do Pythagorean theorem at some point so that we can figure out the radius. But before we can do that, we need to know what x is, because I need to know what the length of this side is. So going back to my picture, I'm going to clean this up a little bit so I can see a little bit better. Going back to my picture, we know that according to that theorem we just talked about up here, if two chords are congruent, which they are, right? They're both equal to 16. That means that their distances to the center are also congruent. So that means 2x is equal to 5x minus 9. So I'm going to use that equation, 2x equals 5x minus 9. I'm going to use this equation to figure out what x is, and then I'll plug it back into this side so that we can do Pythagorean theorem. So let's solve this real quick. So I'm going to move the 5x over here. So negative 3x equals negative 9, which means x equals positive 3. And then if I plug that back into the 2x, 2 times 3 is 6. So that means the measure of this side is 6. And now we can just do Pythagorean theorem to figure out what that radius is. So the radius is our hypotenuse. So we will do a squared plus b squared equals c squared. That would be 8 squared plus 6 squared equals r squared. And then we're just going to continue to solve that. So 8 squared plus 6 squared, that's 100. And then to figure out the radius, we just square root both sides. So r is equal to 10. Okay, so technically, if you remember from the other day, we were calling this like plus or minus 10. But in geometry, a radius is going to be a positive number, so we're just going to count the positive answer for that one. So the radius here would be positive 10. So that problem takes quite a few steps. It involves figuring out the length of this piece that was 2x, so that we could do this right triangle math here to figure out that radius. Okay, looking at another example, this one's very similar. So again, if you're watching from home, I would probably just pause the video and try this one on your own. But I'm going to continue on with this example here. So in the picture, they tell us that JK is equal to LM, which is equal to 24. So that's this chord, right? Here's the chord JK, here's the chord LM. Those chords are both equal to 24. So before we continue, the same exact theorem applies here. So since the chords are equal, that means that these perpendicular distances, these little green pieces here, these are also going to be equal. So at some point, we're going to have to set 3x equal to 7x minus 12, and then we can go ahead and solve for x. I'm going to go ahead and do that first here. So we'll subtract 7x. We've got negative 4x equals negative 12. So x equals positive 3 again. And that's going to be helpful because at some point we are going to make another right triangle for this problem. So same situation, they're asking you to find the radius of the circle. So if I'm looking at the picture, now it doesn't really matter where you make your right triangle. I am going to make mine right here. So I'm going to draw the radius from N to K. So this would be my radius. Okay, so this purple right triangle, again, if it helps, take that triangle and redraw it out here so it's a lot cleaner and easier to look at. So here's my 90. This would be the radius. Instead of writing 3x, I'm going to write down what that actually would equal because now we know that x is 3. So 3 times 3 is 9. So the length of this piece would be 9. And then also across the top here, this side, it's not going to be 24, it's going to be half of 24. Remember, because that chord is being bisected, so that piece would be 12. Okay, same thing here. Now we can just do Pythagorean theorem. So 9 squared plus 12 squared equals r squared. 9 squared plus 12 squared, if you just type that in your calculator, that's 225. And then we can square root both sides, and you're going to get 15. So the radius of this circle is 15. Okay, that's it for the notes. We can go ahead and start the homework.